хороший ли звук. Какие-то подозрительные настройки. Я не уверен, что они правильные. Запустилось. Так, а что там со звуком? Насколько хорошо меня слышно? Как обычно или хуже? По-моему, нормально. So let's briefly return to what we've done at the end of the last lecture. So we defined Hilbert-Sumner function, which we called chi, that depends on some parameter ideal q, and potentially some module. Well, that's an argument of this function, and another argument is the positive or non-negative integer n, and that was by definition the dimension, well, actually in the more general case, the length of the quotient of m by the q to the nm. So, and in the special case where we consider module to be just the ring, we use a little bit shorter notation, just the chi with index q and dependence on n. Okay, so there was another definition that the d of r is the degree. So this function is polynomial. So it's polynomial for n sufficiently large, and d of r is the degree of this polynomial. So this function is called Hilbert-Sumner function if you consider this as a function of n, and when you consider this polynomial, you can call this polynomial Hilbert-Sumner polynomial. And that this d of r is one of the definitions of the dimension of some local Noetherian ring R. So we know already, so proposition that was kind of mentioned last time and doesn't really require proof, it follows immediately from previous proposition that d of r is bounded above by the delta of r, where remember this delta was defined, you consider parameter ideals, and this is the least possible number of the parameters. So this gives us one inequality, and today's goal is to prove a couple other inequalities and combine them together and see that the three definitions of the dimension of a local Noetherian ring actually give you the same answer, and this answer is always a finite number. Okay, so also we tried to prove the following proposition. So let me recall the proposition. So if you take x to be a non-zero divisor or regular element, so if x is regular on the module m, and you say by definition that m prime is the quotient of m modulo xm, so then you have the following inequalities for the degrees of the Hilbert-Sumner polynomials. Well, I'm writing functions, but you're supposed to understand this, that I consider this for sufficiently large n. This is polynomial, so this is degree of the corresponding polynomial. In fact, I think people use this chi as for the function, also for the polynomial, and you need to understand what is it by the context. So we have this inequality. And the proof is actually based on a couple quite elementary observations. And I was missing the first elementary observation last time. So if you introduce notation m to be the xm, so what I was missing is the completely trivial observation that n is actually isomorphic to the m. Yeah, with the isomorphism being just multiplication on x.
X is non-zero divisor, okay.
Yeah, x is not a zero divisor. Okay, so then we introduce notation for the n with the index n, which was just the n intersect with the q to the nm. And well, this is again a stable filtration by the Artin-Ries lemma. So is stable filtration. This is Artin-Ries. And another observation was that we have a short exact sequence. Which is essentially just a combination of the isomorphism theorems. So I think you need second and the third isomorphism theorem to show this. So essentially take the term in the middle, take a quotient by the last term, and apply isomorphism theorem. So I'm going to leave this as a little exercise. Well, we work with the exact sequences a lot, so probably it's not a very hard exercise. So from this, since we have additive functions, we immediately get the following, that the length of the n modulo n with the index n minus the chi m q of n plus chi m prime q of n. This is equal to 0. Well, this is equal to 0 for any n, of course, but for us it will be important this is equal to 0 for all sufficiently high. Okay. So, and then from this what we can see, well, we know that this is a module n which is isomorphic to the m, and essentially we just computing by this term and by this term we're computing the same polynomial. Well, we're computing the same polynomial. We're just choosing the well, that's not like precisely right. So the precise statement would be the modules from this computation and to this computation are isomorphic. The filtrations might be potentially different. So this means that the polynomials might be potentially different, but we proved that the leading term is exactly the same. It doesn't depend on the filtration. So there is a constellation of the leading terms for this polynomial and this polynomial. And that's exactly what we have here. So the degree is bounded by, by the degree minus 1, since we have constellation of the leading terms. So I don't want to write this, so maybe I just finish proof with this. Okay, was it clear? We just cancel leading terms. Well, we prove the proposition that the leading terms doesn't depend on the filtration, and here we use two different filtrations. Okay, so is it true that this is chapter 9, right? So the next 8 or 9? No, 9. So, and I think this is the next section is supposed to be 9.2, right? Yeah. Okay, so 9.2, the dimension theorem. Okay, so maybe I start with the theorem itself. So the theorem, dimension theorem, which is very easy to formulate. So we have local Noetherian ring. We already associate 3 numeric invariants to this local Noetherian ring, and actually these 3 invariants are the same. So the delta of R is equal to the d of R and also equal to the dimension of R. So that's the statement, and the plan of the proof, which is going to take most part of this section, is the following. We're going to prove 3 inequalities. So the delta of R is greater or equal than the d of R. D of R is greater or equal than the dimension of R, and this is again greater or equal than the delta of R. Right? If you can prove these 3 inequalities, then we're done.
I think first we already have.
Yeah. So, and this one we already have. So
dimension is cool dimension.
yeah. So this is the cool dimension. Yes. So we have cool dimension. We have the least number of parameters, and we have something that is associated with the Hilbert-Summerall function. So now we need to prove these two inequalities. Okay, so let's start with the proposition. Okay, I continue to assume that I work with the local Noetherian ring, so I will think about local Noetherian ring, so I'm not going to repeat this assumption. I'm just writing that the d of r is greater or equal than the dimension of r. So I'm proving the second inequality now. So, and this would be a lot like analysis. There will be a bunch of inequalities that we need to combine together. Okay, so proof. So the proof is by induction. By induction on D, which is d of r. Sorry, so the other way around. D of r. Okay, so let's start with the case when d is equal to 0. So if we return to the definition of the d, which was just the degree of the Hilbert-Summerall polynomial, we can say that if you take a length of the ring modulo maximal ideal to some power, right? This is if you consider n sufficiently large, this will be a polynomial of degree 0. Polynomial of degree 0 is a constant. So that's a constant when n is sufficiently large. Well, but this means that for sufficiently large n, we have the following: m to the n plus 1 is equal to the m to the n. But I claim that it is immediately follows from this that the m to the n is 0. Do you see why? Yeah, that's exactly Nakayama's lemma. Recall that in this case, the Jacobson radical is just m. So that's the local ring. So, and I claim that from this statement, it's more or less clear that the dimension of this local ring is 0. Right? Is it so? Just if let's believe the dimension is 0, then the ring is Artinian by the what's called Akizuki-Hopkins theorem that we proved in the chapter about Artinian rings. So the only thing we need to show that in fact from this it follows that the dimension is 0. Well, how we can do this? It's
About if r is Artinian, what does it mean? Like we only need to prove the dimension of r is 0.
Yeah.
We don't need to know that it's Artinian or something like that.
But well, if the ring is Artinian, we know that dimension is 0. So well, argument stays the same. It's just how you interpret this. Well, the argument is quite simple. If you want to show that the dimension is 0, well, you need to show? You essentially need to take any prime ideal, right, and show that this prime ideal is actually this maximal ideal. Well, this is quite easy. So let's take this prime ideal, right? So first of all, okay, P is in the spec R. Well, since this is 0, clearly m to the n is contained in the P. Right, that's a completely trivial observation. Well, now the standard trick, let's take the radical of the left-hand side and the right-hand side. So hence m, which is the radical of the m to the n, is contained in the radical of P, which is still P. I think we've done the same computation last time. So m sits inside P, m is maximal, so m is the same as P. Well, and this is for any prime ideal. So any prime ideal coincides with the m, hence the dimension, oh, by definition the dimension is 0. Or you can say that this is Artinian. So I'm saying that this is Artinian because there's a kind of standard exercise about Artinian rings, that if you take local Noetherian rings, you can characterize Artinian rings by this property. We know if the ring is Artinian, we prove this. And this is an argument that goes in the other direction. So local Noetherian is Artinian if and only if there is some n such that this power is 0. Okay, and this finishes the base of the induction, right? So now we need to do the step of the induction. So I still have some space there. Okay, so let's fix a chain, or so any chain of prime ideals. So P0 sits inside, properly sits inside P1, etc., up to some PR. So is a chain of prime ideals. So let's fix such chain. And also, since we have this proper inclusion, there is an element, let's call this x prime. No, let's call this x. So this is an element in the P1 minus P0. So there is such element. Now I introduce x prime. So this is x. And x prime, well, this is the class of x modulo P0. So x plus P0 that I consider inside the quotient ring R prime, which is by definition R modulo P0. So this is just some notation. Well, so first of all, this is clear that this is not zero ring, oh sorry, not zero element. And also it is clear this is not a zero divisor. Well, this is a prime ideal, so that's the domain. So x prime is irregular. Okay, and since this is a regular element, by the proposition, that the statement of which I just erased, but that I still have the proof of this proposition, we can claim that the d of the r prime modulo x prime is bounded by the d of the r prime minus 1. That's the proposition which we almost proved last time and actually proved this time. Okay, now let's also introduce more notation. So let's m prime be the maximal ideal of the R prime. It's a quite clear application of the correspondence theorem that the quotient of a local ring is again a local ring, so there's only one maximal ideal. Well, then I can, again, essentially using the correspondence theorem, say that if I consider this quotient of the R prime modulo m prime to the n, so this is homomorphic image of R modulo m to the n, right? Since about the
surjection.
Yeah, saying that this is a homomorphic image, you can as well say that there is a surjection from this ring to this ring, maybe with some potential kernel. I think that's a quite trivial observation, but it gives us something. So from this we can say that the length of the R modulo m to the n is greater or equal than the length of the R prime modulo m prime to the n. And since we have such inequalities, if we consider this for sufficiently large n, we can conclude that the degree of the corresponding polynomials have the following inequalities: that the d of r is greater or equal than the d of r prime.
Is this statement for length? It's from like we have a surjection, then we have a short exact sequence.
Exactly, yes. Okay, so we have, maybe I need to use some numbers for this inequality, so maybe it's clear. So I'm just taking this inequality and I can just combine these two inequalities together and get, so therefore I can say that the d of the r prime modulo x prime is bounded by the d of r minus 1, right? So then to this ring, I'm doing this step of the induction, right? So on the D. So to this ring, I can apply the induction hypothesis. So
What if it like d of r prime quotient x prime is like a lot smaller than d of r? Shouldn't we prove like
well, but
more than base, like a lot more base for this?
no, I don't think so. So it says, what you need to show is that we have this inequality. If all my inequalities in the middle of the computations are correct, if I combine them together, I'll get the correct inequality. So there is no problems. So okay, so by induction, so now I can apply the induction hypothesis to the ring r prime modulo x prime. Well, I have the following, that the dimension of the r prime modulo x prime, well, r prime if you want, this is bounded by the d of the r prime. Well, yeah, let me just for shortness just write x prime. X prime. Okay. So we get this inequality. Now the last step of the proof. So maybe I think we need some light. Mm-hmm. Okay, so the last step is the following. We consider the images of the prime ideals, so that we, in the chain that we consider, so I started with some chain, so the images of the P1, up to PR, in the R prime modulo X prime form a chain of prime ideals, of course. Chain of prime ideals of length r minus 1. Well, since I just removed the first ideal and they cannot coincide because again by the correspondence theorem. So we constructed in this ring r prime modulo x prime a chain of length r minus 1, right? Well, this means that if
It can be larger.
potentially, sure, but at least we have an equality that the r minus 1 is less or equal than the dimension of this thing. I think with this you can agree. If you have a chain of length r minus 1, the dimension potentially could be larger. Well, but then what we can do, well, this is bounded above by the d of the r prime modulo x prime, well, by this, by induction. Now for this thing, we take this inequality and just write that this is bounded by the d of r minus 1. And that's the proof. So you can see that this is exactly the statement if you just add plus 1 to the right-hand side, left-hand side. Okay, so in our plan, we proved the second inequality. So maybe what I'm going to do, I'm going to leave the statement of the theorem and leave this plan with the two proven inequalities, and I just prove I need to introduce some notation, and then I just prove this last inequality. So I'm going to erase the statement of the proposition and the proof. Okay. But maybe we can derive a corollary from that proposition, and corollary is the following. So if R comma M is okay. So let me introduce standard abbreviation in commutative algebra. Local Noetherian ring is going to call LNR. So you can find a lot of text with this abbreviation. So if this is a local Noetherian ring, then from this proposition you get the following, that the dimension of R is finite. Since this is bounded by the d of R, and this is also bounded by the delta of R, and these are two finite numbers by construction. So of course there is a natural question, what if I remove this assumption that this is local? If I just take Noetherian ring, is it true that the dimension is finite? Well, in general, no, it's not true. So you can kind of have, you can take the set of all the, say, prime ideals at each localization that's a finite number, but there is no kind of uniform bound for all these numbers, so it could increase to the infinity. And you can explicitly construct a counterexample. I think the first person who constructed the counterexample was Nagata, but the counterexample is quite involved, so we just don't have time to do this. So if you want to see counterexample, I can give you a reference, but I can do this on the lecture. Okay, now I need to give you a definition, so which is quite elementary, the height of the ideal. So the height of P is by the, well, notation is ht, height, and this is just by definition the dimension of the corresponding localization. So let me reformulate this. So in other words, so what's the height? How this is related to the dimension? Well, if you just again use the correspondence theorem for the localizations, where we can say that this is the largest possible chain, such that you start with some P0, then P1, etc. But the last ideal that you can you need to consider is P. So you consider all the change such that the on the right you get P. That's this is the same thing, follows again by the correspondence theorem, because well, when you're localizing at P, you're kind of turning all the ideals, all the prime ideals containing P into the unit ideals. So again, I can say that always height is a finite number, since this is just a local ring.
Like simple is not a prime ideal in ring R, but it will be prime ideal in RP, like great situation.
Mm-hmm.
Is it in other words, zero don't sits in this chain of ideals, but it still will be in dimension RP? How it's like?
No, if you just look at the localization, you take some other prime ideal, not the maximal ideal here. Mm-hmm. Well, you can just kind of use the same idea, but you get a bunch of ideals, but you're supposed to finish at this ideal that you consider. It corresponds to some prime ideal.
Yeah.
Okay, so next proposition. With the same assumption, namely that R is local Noetherian ring, I have the last inequality, that the dimension of R is greater or equal than the delta of R. Proof. So the proof is again by induction, so we construct elements x1, xi, where I is some number. Well, we can start with 0 essentially. Well, with 0 corresponding to a situation where we don't have any elements, and up to d, where of course d is just the dimension, group dimension of R. So we construct such elements, or parameters actually, system of parameters, such that if the ideal generated by these elements is a subideal in some prime ideal, then this prime ideal, so then the prime ideal has height at least I. Okay? So sequence of elements, if you consider any prime ideal containing this sequence of elements, then the height of this prime ideal is at least I. So we're going to construct this by induction.
Oh, we just construct such.
Yeah. So the goal is to construct this thing. Well, essentially because, well, by the induction, we end up with the d such elements, and this will be exactly the system of parameters. So we're going to see then that this will be a prime ideal containing this thing. The height will be at least d, but for local Noetherian ring of dimension d, this is only possible when this p is equal to the m. And in fact, this will be exactly the system of parameters that will generate the parameter ideal. Okay, so of course the base of the induction is completely trivial. So if I is equal to 0, there is nothing to prove. So let's do the step of the induction. So suppose x1 up to xi minus 1 are constructed. So and let Pj, where, well, j is running between 1 and some number s, or any number, that's really important. So what's important that we're going to have only finitely many such ideals. Doesn't matter. So, but I still need to define this ideal. So Pj are minimal primes over this ideal generated by the x1 up to xi minus 1 of height exactly I minus 1. Well, potentially this could be a zero set, empty set. So it is possible that there are no such ideals. But then the proof will be even easier. So, but if there are such ideals, well, the argument is kind of take a quotient by this ideal generated by these elements, then this will be just the minimal primes in the quotient ring, and we know that there are only finitely many minimal primes, since each minimal prime is associated prime, and there are only finitely many associated primes.
Would we take quotient of?
By this ideal.
Why is it like? Okay.
So I'm just proving that there's only finitely many such prime ideals with this property, since they correspond to the minimal primes in some ring, and in any Noetherian ring there is only finitely many minimal primes. Okay. So then, since I minus 1 is strictly smaller than d, which is the height of the maximal ideal, I can conclude that the M is definitely not one of such PJs, right? But then I just use the prime avoidance. Oh, maybe it would be better if I just ask you what I'm using. So, but the conclusion is that M is not equal to the union of such ideals, and this is the prime avoidance. Okay, so then I can claim that there is element xi, so the next parameter with the index I, which lives inside the maximal ideal. Well, I didn't say this, but I hope this is completely clear that elements xi that I'm constructing, they own the maximal ideal. Well, because if they're not in the maximal ideal, this is an invertible element, it's not interesting. So these are all, everything is inside maximal ideal. So then there is element xi in the maximal ideal, and this xi, of course, is not in the union of the pj's, where j is between 1 and s. Okay. So that's the construction of the element xi. Now we need to check that everything works with this xi. So let Q be any prime containing x1 xi. So this ideal. So we need to say something about the height of this Q. Okay, so then Q contains some minimal prime, say P, of the ideal x1 xi minus 1.
Some of pj's.
No, not necessarily. It could be pj, or it could be of the height greater than I minus 1, right? So these are minimal primes with this height, but maybe there is a minimal prime of the height I, or I plus 1, or I plus 10. But at least it is clear that such Q contains some minimal prime. Again, go to the quotient by this ideal, and everything is clear. Okay, now so we have two cases. So two cases to consider. So the first case, as you saying that the this minimal prime is actually pj, right? So then what we have? So then in this case, okay, maybe this is case 1. So then in this case we have xi, which will be in the Q by the definition of Q, and since P is one of these pj's, well, okay, to be precise, for some j between 1 and s. So then xi is in the Q, and xi is not in the P. This is by definition of Q, and by the definition of the xi. So in this case we have the P that sits inside Q, and to emphasize, they cannot coincide because there is xi in one which is not in the other. So then and we know that in this case the height of the P is I minus 1. But if we can add one more ideal on the right, then the height is increasing at least by 1. So hence the height of the Q is at least I. So everything is fine in this case. So the second case, so now we need to assume that the P is not equal to the pj for any j, so for any j between R1 up to S. Well, this is still by our choice of P, this is still a minimal prime of this ideal or over this ideal, right? And by the induction hypothesis, we can say that we know that if this is contained in some prime ideal, then the height of this prime ideal is at least I minus 1. And we already know that this is not of the height I minus 1. So this is our case. So then this height of the P has to be at least I. So my induction height of P is at least I. But Q is even larger, well, potentially larger, maybe coinciding. So it is possible that this Q is actually minimal. And I think there is no contradiction, so we can say that Q is coinciding with P in some cases. But in such cases, well, P already has height y, so height of Q is also at least I. And essentially this finishes the proof of the induction. The base is trivial and we prove the step of the induction.
Can you repeat why this whole induction is proof our proposition?
Well, there's something that we still need to do.
So we didn't do it.
Yeah. Okay. Okay, maybe I now can erase the statement of the theorem and the plan, because, well, when I finish the proof of this proposition, I'm finishing this inequality, so I'm finishing the proof of the main theorem. Okay, so what we get by this induction? So of course, for the proof of the proposition, the interesting case is when I is equal to the d. So then we construct the system of parameters. I didn't actually mention this. There is another standard abbreviation in the commutative algebra, SOP, for the system of parameters. So we have system of parameters x1, xd. So this is, well, if this sits in some prime, right, by the induction, we can say that the height of the prime is at least d. But it is absolutely clear that in this case this means for a local ring that the b is equal to the m. Okay, so the last question, how this is a system of parameters? So why I can say that this sequence of elements with this property is actually a system of parameters. So remember, by definition, this means that they're supposed to generate a parametric ideal. And there was 4 equivalent definitions of a parametric ideal.
So we have to prove that they generate the maximal ideal in this case.
I don't think that this is in general true.
It's like that our quotient B should be RT, the type of.
Yeah, so one of the possible things to say is if you take a quotient of your ring by this system of parameters, what's left is an Artinian ring. That was one of the possible definitions, but there was actually, I think, 3 more. So you need to choose one and say why this works. And I think one is much easier than the 3 others. So essentially what we need to say that this system of parameters, well, these elements, well, to say that this sequence of elements is a system of parameters, we need to say that they generate M primary ideal. So I think the easiest way to say this is to check that the radical of this thing is the maximal ideal. Right, so I claim that if I take the radical, then I'll get exactly the maximal ideal. So what's the radical of an ideal? It's intersection of all prime ideals containing it.
Oh, no prime ideals
And
containing.
there is only one. So we proved the last inequality and the dimension theorem with this inequality. So let's derive some corollaries from this. So what we have dimension of R is bounded above by the dimension over K M modulo M squared. So of course K here is just the it's just the quotient of R modulo M. So the crew dimension of the ring is bounded above by the dimension of the vector space.
Is it residue field here?
Yeah.
And this figure, why is it? Is clear, why is it?
It's almost clear, so it requires little proof. So depth?
Yeah, there's some in logical algebra depth. It's something like dimension. Like, I don't.
The depth is just the length of a maximal regular sequence.
Yeah.
It's kind of a little bit different than this.
Okay.
Yeah, so what we really need to show that, well, let's fix some notation. So let's say that xi in the M, where I is again between 1 and s, this is just the elements such that xi plus m squared form a basis in the quotient. Okay? So I'm saying that essentially I'm saying that this is a vector space of dimension s, and I'm choosing some specific basis, right? So then I need to show that the dimension of R is bounded by this S. Okay, so then I can say that M is generated by these elements. Do you see why? Yep. This is again by Nakayama's lemma. But then this is essentially the end of the proof, right? Because, well, I can think in terms of the dimension of R, or I can use another invariant, the delta of R, which is the least number of the parameters. So here I constructed S parameters, where S being dimension of the right-hand side. So the least number of the parameters, well, at least this is bounded by this S. So delta of R, which is equal to the dimension of R, and this is less or equal than S. We always have that the maximal ideal is a parameter ideal. Quotient by the maximal is just a field, so the length is finite. But it is possible that this number S is not exactly the least number of parameters that you need in the ring. No, there are examples that, for example, where this is 1 and this is 2, well, essentially any number, well, not any number, well, there are restrictions. But at least I can give you an example where left-hand side is 1 and right-hand side is 2. So you consider, say, a cubic curve like this. So which is singular at this point. Well, you can compute in this case that the dimension, well, actually, to get the local ring, well, you need to do something like you consider R to be formal power series in two variables. Unfortunately, we didn't have time to discuss formal power series. It's a chapter about completions, and we don't have time for this. But here you take a quotient by, well, some cubic polynomial. I believe this is y squared minus x times x minus 1, x squared. So I think something.
It should be x plus 1.
Well, I want my root to be at the point 1. No, yeah, you're right, plus 1. So it's not actually a hard exercise. Well, geometrically, this is a curve with potential singularity at the origin. So it's not very kind of surprising that the Crook dimension in this case is actually 1. Which
Local.
it is local because I take the formal power series. But if you try, so in this case the dimension, so the Crook dimension of R is 1, but taking local essentially means that I kind of consider only some small neighborhood of the origin in some sense. Well, it's not, of course, correct in the Deriski topology, but
Yeah, I think if you take like open
Yeah, in the risky topology, that's definitely the case. This is why we need completion. So completion is kind of looking very, very locally. It is not possible in the risky topology. So anyway, so the dimension will be 1, but the right-hand side, so the dimension of the m modulo m squared, well, you essentially can see this if you consider kind of it will be generated by these two vectors along these two branches. So it will be 2 exercise to actually compute this.
We just found what is intersect, like degree of intersection, I think, something like that.
No, essentially the idea here is that, well, this is just a crude dimension, there is no idea here, and this thing is the cotangent space.
Cotangent.
Yeah, cotangent space for the variety corresponding to the ring R at the point corresponding to maximal ideal.
Actually, for plane curves, the number on the right coincides with the multiplicity of the point in the curve. If you define it as, well, if you have a nominal, you change coordinates so that your point you're looking at is at the origin,
Mhm.
and the multiplicity of it is, well, the least degree of a monomial, which
Okay, yeah, you can do this, yeah, sure.
yes, and the number on the right coincides with the multiplicity of this point. So it's kind of
Yeah, but in general, for varieties of any dimension, you can just give one of the possible definitions. This is a cotangent space at one particular point. Yeah, and the idea behind this inequality, and there is also some notation for this. This is sometimes called,
It's embedding, yeah.
Hmm?
It's embedding dimension.
yeah, it's EDIM, so embedding dimension. And this corresponds to the situation where kind of, when you embed this ring, so say you have a curve, how you can embed this in the two-dimensional space and three-dimensional space, if this is only to the two-dimensional space, but not one-dimensional, this is 2, three-dimensional, this is 3.
So yeah, I understand that for regular, we have for regular rings we have all equalities.
Yeah, so it is one of the definitions of the regular ring. So regular meaning that there are no singularities. So and this one of the ways to define this is just to say that the dimension is the same as the embedding dimension.
And this have a lot of dimension that
Yeah.
are equal.
Yeah, and this is quite natural from the geometrical point of view. You want to say that your variety is regular at some particular point if the dimension of the tangent space is exactly as the dimension of the variety,
Dimension of what?
of variety itself.
For
So this is, for example, what you see for smooth manifolds in the analysis of manifolds. And here, since you have this singularity, this is not smooth at this point, so there is a dimension 1 for the variety. This is still one dimension, but there is a kind of high dimension for the tangent space. And that's exactly the situation where you have something singular.
May I ask,
Mhm.
like for parabola, we don't have singularities, yes?
Parabola smooth, yes.
Yeah, parabola is smooth. So embedding dimension for parabola, since will be 1.
Yes.
Yes. So it's like we can find like embed parabola into one-dimensional space. That means like that.
Well, if you kind of,
does it have something to do with that equality can be parameterized?
yeah. So you can think about the parameter that is essentially just a fine line, which is embedded in some interesting way into two-dimensional fine space.
And we parameterize this curve.
Well, think about what will you do around the singularity?
I don't usually.
No, actually, remember we discussed this case when y squared is equal to the x cubed, and that was the same as the ring generated by the t squared and t cubed. So in some sense, you can think about this ring as a parameterization, but this parameterization is not isomorphic to just k of t. So it's not a parameterization of by the affine line.
Of one.
Well, I don't think that in general parameterization is something that works nicely, so I wouldn't go in this direction. So I would say that, well, you just can, you can believe that somehow you can compute this number and just compare them and just ask, is it true that they are the same? Okay, so there was another elementary observation, so which is the following. So now I assume that R is Noetherian, not necessarily local. We take several elements, so R elements in this ring R, and take minimal prime. So if P is minimal prime over ideal generated by these elements. So in other words, we just take an ideal with R generators and take any minimal prime over this ideal. So then the height of P is bounded above by the R. So we have such an equality in general. And this is not very hard to derive, again, from the dimension theorem. So let's fix some notation. Well, just not really fixing notation, just rewriting what I have. So I have this ideal generated by the R elements, and this sits inside some prime ideal P. So clearly, from this I have, if I do the localization at P, I'll get ideal generated by the same elements. But now inside the local ring RP, this sits inside the PRP.
Why when we localize doesn't go to 0? Like, it doesn't matter.
Well, if some of the generators are 0 in the localization, the inclusion is still correct. So what's important, well, this is the unique maximal ideal, right? So what's important, this is not a unit ideal, but that's clearer since we have this inclusion. So let's do our favorite trick. Let's compute the radical of the right-hand side and left-hand side. So the radical of the left-hand side, well, is something, and on the right-hand side, well, this is a maximal ideal. Maybe let me just fix notation. So this is MP. So this is still MP. The radical stays the same. So what we can okay. Yeah, so well, the inclusion is not very interesting. It's completely trivial, but I claim that they are actually equal, and this is because this is the minimal. So again, if I consider all the prime ideals, well, containing this, and this is the intersection of all such prime. Well, if I want to compute the radical, well, I need to take the intersection of all the prime ideals containing this thing. And if here in the ring R itself, potentially there are other minimal primes, but when I do the localization, they all turn to the unit ideals. So there's only one. So what we have here is actually a parameter ideal for this local ring. So, and this system of elements is, so this is the system of parameters.
Dimension of RP, I think, is R.
So it is the same.
No. We only from this we only get the inequality since we constructed, well, some R parameters, but the invariant delta is the least number of the parameters. So this is why we have just inequality, not equality. Right, so we know that R parameters is enough. So the height of P, which is the dimension, is the least number of such parameters. So it's definitely bounded above by the R. But in general, we cannot conclude that they're equal. So height of P is bounded by the R. So next corollary, which actually have a special name. So corollary. So this is Grove's principal ideal theorem. So as before, R is Noetherian. We fix an element x in the R, which is neither a zero divisor nor a unit. To avoid this trivial case, I don't want to consider unit ideal. And
Why does it exist?
well, if there are no such elements, then you just don't have a meaningful statement. So in the statement, you start with a ring and such element. So then you have the following. So then if P is a minimal prime of a principal ideal, hence the name principal ideal theorem, then height of P is precisely 1. Well, first of all, we already know that the height of P is bounded by 1, right? By the previous observation. So we only need to understand that if height of P is 0, then something is not working. So we need to exclude this case. Well, I claim that it is clear that if the height of P is 0, well, what you can say about such P anyway?
Then it's all consists of zero divisors, I think.
Why?
Well, we can localize this and
We'll get an Artinian ring.
I think we get everything will be nilpotent because everything should be consist in nil radical. And there is nil radical intersection of all primes and there is no primes.
We have proved that a local Artinian ring, in local Artinian ring, maximal ideal is not potent. And the condition that height of P is 0 is precisely that the localization of P is Artinian. So everything in P is a maximal ideal localization was not
Potent, this means that everything of P is zero divisor, that means X is zero divisor.
Yeah, so that's one of the ways to say this. Well, actually, what I wanted to say, well, is more or less the same, but a little bit different. So I wanted to say that if the height of P is 0, this means that this P is minimal. But if this is minimal, this is associated prime, right? So from this, we can say that P is associated prime of the R, and the set of zero divisors of R is just the union of all the P which are associated primes, right? But anyway, so everything is zero divisor in this P. By this argument or by your argument, this also works. So that's a contradiction. So hence, X is in the space of zero divisors of R, and that is not possible. Okay. So next corollary. Now I need a local Noetherian ring, so L and R. Let's take X in this R to be regular. So in other words, not a zero divisor. So then if I look at the dimension of the R modulo X, I will get the dimension of R minus 1. Quite, I think, quite natural property that you would expect. And saying that the dimension of a hypersurface is dimension minus 1.
And the X is regular means that it is not a zero divisor.
Yes.
And it also shouldn't be a unit, right?
Yeah, so it's also not a unit, well, because if this is a unit, this will be just a zero ring, so not a unit. Okay, so first set D to be the dimension of this quotient ring, and by the dimension theorem, this is the same as the degree of this of the Hilbert-Summerall polynomial. So this is D of the R modulo X, and for this thing we already know that there is an inequality. So this is bounded by the D of R minus 1. So this is, again, by the dimension theorem, this is dimension of R minus 1. So this gives us inequality in one direction. So we need somehow to derive an inequality in the other direction. So there are elements x1 xd in the M. Okay, so let's take such elements such that if you consider such that if you consider x1 bar xd bar, and this is in the R, so this is corresponding classes in the R modulo X, right? So I want this to be I want this to be M modulo X primary.
So they generate a parameter ideal for...
Yeah, this is a system of parameters for the quotient ring, and since this is a quotient ring, I can always present them as a classes of some elements in the R, in the M.
There exists such.
Yeah.
Why?
Well, since I know that there is a system of parameters with d elements in the quotient ring,
Also, we take in quotient ring some system of parameters, and
and any element in the quotient ring is of this form. So this is just because the quotient ring. Okay. So then I claim that if I consider x, and then I take just x, and then I add x1 up to xd. So I get d plus 1 element. So all the elements that we have before plus this x that is regular element. So I claim this is M primary. So let me just say that if you get this, then d plus 1 is bounded, is greater or equal than the dimension of R. And this finishes the proof. So the only thing we need to understand is why this is true.
gets radical. Take a radical. Usually we do it like this.
Well, I think maybe in this case the radical is not the most convenient way.
Probably the condition that maximum ideal to some power is contained in
Yeah, I think this works. And also probably it's not very hard to convince yourself that if you take a quotient by this thing, the length is finite. Since you already know that when you take a quotient by x and then you take a quotient by the rest of this thing, you get something of finite length. So kind of combining this again by the isomorphism theorem, you can see that the quotient by this system of elements is something of finite length.
Can you repeat all proof for this?
For this? Well, what I was saying is the following. You have this ring, we take this d plus 1 elements. If you want to say that this is M primary, equivalent condition is to say that the quotient of the, the length of the quotient by this thing is finite.
Because then it will be articulate.
Yeah. So, but you already know that if you take first quotient by x, so you get a ring R modulo x. So this classes of this thing, if you take quotient by the classes of this ring, this will be of finite length. So also finite length. Yeah. Okay, so actually it's only 9 minutes left and it's not enough to start a new section, so I think we just end here. Yeah, so this is the last statement and the last lecture and the end of the course. So maybe I just use this a couple of minutes to kind of give you some other directions what you can read if you want to study more commutative algebra. So first of all, there is a chapter about the completions that is missing in this course. I was hoping that I have time to say something about completions. So maybe you can read a chapter about completions in essentially in any book. So A.T. MacDonald works. Also Eisenbach's books has quite fine chapter about completions. There is a Hensel's lemma, which is probably the most important statement about the completions. So then when you learn completions, well, there are several other things that I didn't even plan to do, but it's quite important in commutative algebra. So that's information about regular sequences and related notions of Kazoo complex, some little homological algebra in commutative algebra. So, no, I would say this homological methods in commutative algebra. So regular sequence, Kazoo complex, depth, its relation to the X, and the notion of Cohen-Macaulay module, Cohen-Macaulay ring, regular ring, Gorenstein ring, complete intersection ring. So you can read.
What's your reading it like year? Year. What's your reading it in year from?
So next year.
Yeah, like in homological algebra.
Probably I'll mention something of that, but I won't have enough time to do all the details. So if you want to read about this, I suggest you use Matsumuro's book. I think it's chapters 5 and 6.
I think in Weibull also a lot about, not a lot, but some about Cohen-Macaulay rings and Grok.
I would say it's not such clear as in Matsumuro's book. I would prefer Matsumuro's. So chapters 5 and 6 about regular sequences and notions that you can derive from that. And one more interesting basic topic in the commutative algebra is scalar differentials. This is something like cotangent bundle in analysis, tangent cotangent bundle. So scalar differentials and derivations. Nice introduction, I think, is Eisenbach's book. I think it's chapter 15 or 16, something like that. Well, that would be the basic topics that you kind of might need if you study algebraic geometry, if you want to apply commutative algebra. But of course, there are many other topics in commutative algebra, but I would say not as important as what I mentioned. Что-то там, commutative ring theory.